This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 2 of the Dance of Particles. In this episode, titled The Higgs Boson, the Particle That Gives Mass, we'll unravel the fascinating role of the Higgs boson in the universe and why it's essential for our understanding of particle physics. So, let's dive in. Right now, as you walk, breathe, or drive, an invisible field is quietly deciding how hard it is to push the world around. In this episode, we'll step into that hidden arena and meet the shy particle that proves this field and gives matter its heft. In 2012, two gigantic detectors buried under the French-Swiss border quietly made history. Atlas and CMS, each the size of a cathedral and packed with millions of sensors, saw the same faint, stubborn signal, a new particle flickering into existence and vanishing in a fraction of a trillionth of a second. This was the Higgs boson, the long-suspected tip of an unseen iceberg. What made that moment extraordinary wasn't just adding one more particle to a cosmic inventory. It was the sudden confirmation that a background mechanism we'd only inferred on paper was actually real. Like finding a tiny key that fits every lock in a vast theoretical blueprint, the Higgs tied together why some particles cling together to form atoms and stars, while others barely interact at all. In this episode, we'll follow how scientists trapped that fleeting key, weighed it, and asked, is this all there is, or just the doorway to deeper layers of reality? Your challenge this week: each time you encounter something heavy or hard to move, a door, a suitcase, a packed bookshelf, pause and briefly ask yourself, what would this be like if the Higgs mechanism didn't exist? Don't just shrug and move on. Try to picture which familiar structures around you would no longer hold together or even form in the first place. By the end of the week, pick one everyday object and write a short, concrete description of how its existence depends on particles having mass at all. To see why this discovery shook physics, shift the focus from the particle itself to the framework it completes. The Higgs wasn't predicted as an afterthought, it was woven into the standard model decades in advance, like a missing line of crucial code in an operating system. When Atlas and CMS finally caught its signal, they weren't just spotting something new, they were stress testing that entire blueprint under extreme conditions. Now that the particle's mass and basic properties are measured, the real tension begins. Do they match the script exactly, or hint at subtle bugs pointing to deeper, hidden laws? When physicists talk about the Higgs field, they don't mean a rare, exotic ingredient switched on only in special places. They mean something more radical. The rulebook says this field must be on, everywhere, all the time, even in the calmest vacuum we can make. That constant background value quietly reshapes how certain particles behave, in a way you can't turn off without breaking the mathematical symmetries the theory starts from. Here's the twist. The equations are originally written so that key particles should be massless. The symmetry that keeps things neat and calculable actually forbids explicit masses. Instead of throwing that symmetry away, physicists use a more devious move called spontaneous symmetry breaking. The underlying rules stay elegant and symmetric, but the actual state the universe chooses looks lopsided, like a perfectly round stadium whose crowd spontaneously gathers in one corner. The Higgs field settling into a non-zero value is that crowd in the corner. Once that happens, several things lock into place at once. The W and Z bosons, which carry the weak force, pick up large masses, while the photon stays massless. Fermions, such as electrons and quarks, gain their masses through adjustable interaction strengths with the field, different for each species. Those interaction strengths, Yukawa couplings, are simply inputs to the model. We don't yet know why they take the bizarre pattern they do, spanning many orders of magnitude. The particle discovered at the LHC is a ripple in this already settled field. Collisions don't create the background itself, they momentarily kick it, producing a localized excitation that quickly decays. The ways it is produced, and the channels it prefers when it disappears, encode how strongly it talks to other particles. That's why experimentalists obsess over tiny deviations in its production rates and decay patterns. Any mismatch with precise calculations could signal extra fields, hidden particles, or novel interactions influencing the whole process. And here's the deeper question the discovery sharpened instead of solved. Why this field, with this specific non-zero value and this peculiar pattern of couplings, in this universe at all? Think of a software platform that ships with a built-in performance governor. Every app runs on the same hardware, but the governor dials how much CPU or memory each process really gets. Some programs are granted huge resources and feel heavy. Others are throttled and stay light and quick. In our universe, particles play a similar allocation game. They all live in the same underlying framework, yet each one negotiates a different effective setting, which we see as a different inertia when pushed or accelerated. This resource allocation view helps explain why particle physicists care less about a single number and more about patterns. If one application on this cosmic platform behaves oddly, say, gets more performance than the governor rules should allow, that glitch hints at extra code running underneath. In practice, that means comparing ultra-precise collision data to calculations and hunting for stubborn discrepancies that don't wash away with better measurements or refined theory. 125 billion electron volts sounds abstract, but this particular number quietly shapes cosmic history. That field's setting helped decide how atoms formed, how stars burn, even whether stable chemistry exists. Shift it slightly and galaxies might never condense. Your challenge this week: whenever you see something stable in daily life, a bridge, a habit, a market, ask what hidden settings make it so, and how fragile that stability might really be. So the real payoff isn't just finding the Higgs, but using it as a probe. Its measured traits fence off entire families of speculative theories, much like zoning laws quietly shape a city's skyline. Future colliders may nudge those fences, revealing side streets in physics where dark matter, new forces, or extra dimensions could be hiding in plain sight. Try this experiment. Grab a strong magnet, a small metal object, like a paperclip, and a plastic object, like a pen cap, and move the magnet slowly toward each one, noticing how only certain kinds of matter feel the magnetic field. Now, imagine an invisible Higgs field filling the room the same way, but interacting with particles based on their type rather than their material, giving some lots of mass, strong interaction, and others very little, weak interaction. To make it visceral, push an empty box across the floor, then the same box filled with books, and compare how much harder it is, just like particles that interact more with the Higgs field feel heavier and are harder to accelerate. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!